This is Ham College, episode 98 for March 3rd, 2023. Ham College is brought to you by Icom. Got cabin fever? Look no further. Spring is just around the corner, and Icom has what you're looking for. Our top quality base stations, mobiles, and handhelds are perfect for working your favorite bands inside the ham shack or venturing out this spring. Good evening, everyone. Welcome to another episode of Ham College. I'm Professor Thomas.
And I'm Dean Martin.
And boy, we've got some toughies for you tonight. This last time, I don't even remember what we talked about last time. Do you?
Yeah, I remember. We talked about DSP filtering and other operations, software-defined radio fundamentals, DSP modulation, and demodulation.
That's what we're going to talk about.
Yeah, I knew it seemed kind of familiar.
Were you
How
here?
about if we talked? This said previously recorded at the beginning, didn't it?
Yeah, but not anymore. Last month we talked about modulation and demodulation, reactance, phase, and balance modulators, detectors, and mixer stages. What is meant by direct digital conversion as applied to software-defined radios? A. Software is converted from source code to object code during operation of the receiver.
B. Incoming RF is converted to a control voltage for a voltage-controlled oscillator.
C. Incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal.
Or D. A switching mixer is used to generate I and Q signals directly from the RF input. What is meant by direct digital conversion as applied to software-defined radios? Software converted from source code to object code. That's not it. I've written enough source code and generated enough objects to know that's not even close. Incoming RF is converted to a control voltage for a voltage-controlled oscillator. Incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal. That seems plausible. Switching mixer is used to generate I and Q signals. I'm going with C because I think the others are not it. C, incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal. The analog to digital converter is what's grabbed me.
Okay. I'm going to agree with you as most of the chat room does. There was a D in there. And D, that sounds pretty close too, because that I and Q signal stuff is sort of software-defined radio related, but I believe you're correct. It's C.
Well, that's not bad for a guy that didn't know anything for the first one. Don't get too used to that, though.
If we look at the top, that's a super heterodyne system. In this case, they're showing a block diagram of an IC7600. Starting on the left, the antenna feeds into a bandpass filter. That is mixed, where the little X is in a circle there, with the first local oscillator. And then that goes to a hybrid that splits the signal out two ways. The green box around the top portion of that block diagram, that's the receiver. The orange box, that's a little bit below that, that's feeding the real-time spectrum scope display on the radio. A real old super heterodyne radio wouldn't have had that, but the 7600 did. The hybrid splits the signal out two ways after it's been mixed with the first local oscillator. If we stay at the top there inside the green box, it goes into a crystal bandpass filter, which is called often roofing filters. We mix it again with the second local oscillator that changes the frequency again. That is fed to the A to D converter, converts that analog signal into digital. Then it goes to the DSP section where we've got noise reduction and various other functions that we can do to the received signal. Then it goes to the digital to analog converter, which converts it back to analog since no one's ears are digital, they're all analog. That goes on out to the speaker. Right below it in the sort of pink box there, RF direct sampling system. That's what Icom calls it. It's the same thing as direct digital conversion. We've got the antenna that feeds into a bandpass filter, just like with a superheterodyne. Rather than go through any local oscillators, it goes straight from that bandpass filter, right at the RF frequency, into an analog to digital converter. It's immediately digitized. Then it goes through a fill programmable gate array, an FPGA. It's split two different ways from there. If we stay inside the green box drawn around it, straight into DSP, where we've got noise reduction, bandwidth adjustments, all the neat little features you've got on the receiver. Then it goes to the digital analog converter on out to the speaker. And if you notice, there's less stages there, and that signal is not being shifted down in frequency with a couple of local oscillators up front. It gets digitized immediately.
What kind of digital signal processing audio filter is used to remove unwanted noise from a received SSB signal? A. An adaptive filter.
B. A crystal lattice filter.
C. A Hilbert transform filter.
Or D. A phase inverting filter. Wow. Now, this right here could be a little tricky. I'm going to rule out some first. I don't think it's a crystal lattice filter. If we're doing digital signal processing, I don't think we would need that. Those are used, but not really in DSP audio filtering that I know of. A Hilbert transform filter, that sounds digital. A phase inverting filter, that sounds analog to me. And back at the top, an adaptive filter.
Whatever that means.
Whatever that means. And that's the one I'm going to go with. It's an adaptive filter that's used.
Why?
With DSP audio filtering.
What's your reasoning?
To remove unwanted noise and receive single sideband signals. What does the chat room say?
A.
You asked me what was my reasoning for that answer.
I did.
An adaptive filter is a system with a linear filter that has a transfer function controlled by variable parameters. Because of the complexity of the optimization algorithms, almost all adaptive filters are digital filters. Adaptive filters are required for some applications because some parameters of the desired signal processing operation, for instance, the locations of reflective surfaces and a reverberant space, are not known in advance or they're changing. The closed-loop adaptive filter uses feedback in the form of an error signal to refine its transfer function. And there's a lot more I could say about that, but let me just give an example here. Say you're recording a heartbeat or with a ECG signal. It could be corrupted by noise coming in on the main AC lines. So you got a hum mixed in there along with the heartbeat. And the exact frequency of the power and the harmonics may vary from moment to moment. So you can't say that we're just going to put a 60 hertz notch filter in there and that's going to exactly remove it. It would help, but it's also going to remove the heartbeat signal, part of it as well. One way to remove the noise is a filter with a notch, which I was just saying, at the mains frequency and its vicinity, but this could excessively degrade the quality of the ECG, since a heartbeat would likely also have frequency components in the rejected range. To circumvent this potential loss of information, an adaptive filter could be used. The adaptive filter would take input from both the patient and from the mains and be able to track the actual frequency of the noise as it fluctuates and subtract the noise from the recording. Such an adaptive technique generally allows a filter with a smaller rejection range, which means in this case that the quality of the output signal is more accurate. We're getting a sample of the signal we want along with a sample of the noise, and then just canceling the noise signal out or removing it. And we're left with, in this case,
standard noise
just
reduction.
Huh?
Just standard noise reduction.
Standard noise reduction?
Well, isn't that what noise reduction is? Digital noise reduction? You get the noise sample, and then you basically...
If you're using an adaptive filter, yes.
Like in Audacity, when you're going to do noise reduction, you go find a sample of the noise without the audio that you want to keep in it. You grab that, and then it'll process the whole file, and it basically nulls out that.
And it's using an adaptive filter. It doesn't say adaptive filter, but
it's got to be, because that's basically what's happening.
Yeah. And our DSP noise reductions on rigs work that way too.
Mm-hmm. It's pretty cool stuff.
It is pretty cool stuff.
I have to commend you for building the virtual wall so fast when the laughing started.
Yes.
I saw it come up right there, and then it went right back down after you finished.
Yeah. I had to focus here on the paper. I heard you snickering over there, but I wasn't going to look because I knew what would happen.
Yep. It's contagious.
What type of digital signal processing filter is used to generate an SSB signal? A, an adaptive filter.
B, a notch filter.
C, a Hilbert transform filter.
Or D, an elliptical filter. Well, it's not an adaptive filter. We just talked about that. It's not a notch filter. We've done those before around here. We just talked about that too a little while ago. So that leaves me C or D, Hilbert transform filter. That should be called Dilbert, not Hilbert. Or an elliptical filter, which I'm not sure what an elliptical filter is either. So I'm going with C or D. I might have to narrow it down closer than that, aren't I?
A little bit.
Okay. Well, it's 50%. I'm going to guess it's going to be C because I have no idea what it is, and that's a kind of a cool sounding name.
I'm going to agree with you. It's a Hilbert transform filter. And I actually...
Well, I knew good and well it wasn't A or B.
What if I just happen to have something on a Hilbert transform right here?
Mind blown.
The Hilbert transform of a signal is often referred to as a quadrature signal, which is why it's usually denoted by the letter Q. Electrical systems which perform Hilbert transforms are also known as quadrant filters. There's that Q. These filters are usually employed in systems where the signal is a continuous wave or a narrowband signal, like a signal whose bandwidth is a small percentage of the dominant carrier frequency. A quadrature filter is mostly used in systems where frequency demodulation is required to extract a baseband signal from a narrowband signal.
What is a common method of generating an SSB signal using digital signal processing? A, mixing products are converted to voltages and subtracted by adder circuits.
B, a frequency synthesizer removes the unwanted sidebands.
C, varying quartz crystals characteristics emulated in digital form.
Or D, signals are combined in quadrature phase relationship. Let me read the question again because I wasn't really paying attention. What is a common method of generating an SSB signal using digital signal processing? Okay. Well, this can narrow it down.
Well, I think you might have just told us.
I think I might have. A. Mixing products are converted to voltage and subtracted by adder circuits. No. B. A frequency synthesizer removes the unwanted sideband. No, a frequency synthesizer would be a generator. How's that going to remove anything?
If
C.
you generate it out of phase and null it out.
It doesn't say you add it back.
That's true.
C. Varying quartz crystal characteristics emulated in a digital form. No, I mean, that sounds like a neat trick, but I'm not sure that would be advantageous. But D, signals are combined in quadrature phase relationships. Yeah, if we've got our signal in a quadrature phase relationship, I'm just going to say
Well,
D,
that's what the
and then
paper
we'll
said a while
explain it.
ago. It's got to be
Is
right.
it? Oh, yeah, quadrature phase. Well, we were talking about Hilbert transforms there.
Yeah,
I'm going to say it's D.
but it's a single sideband question, so.
Yep. And what does the chat room?
D. D.
Okay.
Yep. Can't fool those guys, man. They're
Not
going to
usually.
pass their extra test easy.
Well, you know, they're doing a lot better than I thought they would.
You're doing a lot better than I would. I have.
No, that's
I've
no.
been struggling.
I'm not saying anything bad about them. I'm just observing, based on my own experience with these questions earlier. With quadrature modulation, the term IQ is often used for in phase, I, or Q for quadrature, and that refers to two sinusoidals that have the same frequency and are 90 degrees out of phase. The I signal is a cosine waveform and the Q signal is a sine waveform. A sine wave is shifted by 90 degrees relative to a cosine wave. In other words, the sine and cosine waves are in quadrature. IQ signals are always amplitude modulated, not frequency or phase modulated. Any form of modulation can be performed simply by varying amplitude, only the amplitude of I and Q signals, and then adding them together. So we're not varying the phase, we're only varying the amplitude of them. If you take I and Q signals of equal amplitude and add them, the result is a sinusoidal with a phase that is exactly between the phase of the I signal and the phase of the Q signal. Single sideband has the mathematical form of quadrature amplitude modulation, or QAM, in the special case where one of the baseband waveforms is derived from the other instead of being an independent message. So there we got some IQ or quadrature modulation going on. The phasor diagram, or the phase between the two signals, is shifting as those two waveforms change phase from each other. Any signal you've got, if you break it down with I and Q, it's going to show up somewhere on that phasor diagram. You know, you've got an amplitude and you've got a phase, and you just pick out the point along there and you can recreate any waveform you want. How frequently must an analog signal be sampled by an analog to digital converter so that the signal can be accurately reproduced? I know you're going to know the answer to this one.
You think
A, yeah, at least half the rate of the highest frequency component of the signal.
B, at least twice the rate of the highest frequency component of the signal.
C, at the same rate as the highest frequency component of the signal.
Or D, at 4 times the rate of the highest frequency component of the signal. How frequently must an analog signal be sampled by an analog to digital converter. So that's going to be. I don't know why it makes you think I would know this one. I want to say it's twice the rate. I'm gonna go with B. I may get buzzard,
Okay.
but I'm not sure.
is you may get buzzard. Is that what happens when you drink out of a green can?
Yep. The buzzard circle.
You're right. It's B. You want me to tell you how you can, and the reason I thought you would know the answer to this?
What makes you think I would know that?
Because you and I used to do a lot of digital audio programming together.
That's been a long time ago.
Yep. On a WAV file, if you ripped a CD, or let me say the sample rate used on a compact disc, what is that sample rate?
44.1 kilohertz.
Yep. What's the highest frequency a human can hear? The one that can still hear?
About 22.
About 20. So it's about twice. At least twice the rate of the highest frequency. And that figures out there.
Well, I never really put that together like that.
Yep.
What is the minimum number of bits? Oh, you should know this one.
Or payback, right?
What's the minimum number of bits required for an analog to digital converter to sample a signal with a range of 1 volt at a resolution of 1 millivolt? A, 4 bits.
B, 6 bits.
C, 8 bits.
D, 10 bits. You know, I don't know where it came from. It just stuck in my head. The girls on the school bus screaming a cheer, something about 2 bits, 4 bits, 6 bits, $1.
Yeah, unfortunately, that went through my head too when this was going.
What is the minimum number of bits required for an analog to digital converter to sample a signal with a range of 1 volt at a resolution of 1 millivolt? All right, we can deduce that down. Part of it pretty easy there. If the highest signal we can measure is 1 volt, and we're going to measure it in 1 millivolt increments, or resolution of 1 millivolt.
1,000th of a volt.
That means our number is going to need to be able to handle 1,000. All right. That's in decimal.
Okay, that makes sense.
All right. So how many bits would it take to store that number? I'm going to say it's D.
10 bits.
It would take 10 bits. You jumped right on that one. That's because you do a lot of ciphering. I can tell. You're just that kind of fellow. So I'm saying it's D. Let's see. The chat room.
I'll don't D in there.
Yeah. There's a lot of D in there. Let's pull up a nearby scientific calculator. And I say we're going to need 1,000.
Yep.
Well, let's change it from a scientific calculator to a programmer's calculator, which is what we're going to need. And yeah, you're probably not going to have a programmer's calculator with you at the test, but this is just the easiest, quickest way I can explain it. If we're talking about bits, we're talking about a binary number. All right, so I'll select binaries, and that means each bit is going to have to be a 1 or a 0. If we just had a 1-bit number, look here where it says decimal. The highest number we could store would be a 1. If we had a 2-bit number, the highest number would be a decimal 3. If we had a 3-bit number, the highest number you could store would be a 7. A 4-bit, you could store the number 15. If we go on up, 5, 6, 7, 8, 9, 10 bits, we could store a decimal 1023, or 1024 is how you'll see it.
Zero base.
It took 10 different bits to get a number large enough to store the 1,000 points that we're dealing with. What function is performed by a fast Fourier transform? A, converting analog signals to digital form.
Oh, I got this one. B, converting digital signals to analog form.
C, converting digital signals from the time domain to the frequency domain.
Or D, converting 8-bit data to 16-bit data. It's going to be C, converting digital signals from the time domain to the frequency domain.
You just jumped all over that one.
Well, I knew what this one is.
Okay. Well, let's see what the chat room. Oh, they're saying C. I'm going to agree with you.
Yeah, that's easy.
You got it. So, you want to do some explaining on that one?
I can't really explain it. I know it's on
Sure
my
you can.
oscilloscope.
There you go. You can explain it.
Oh, yeah. It's just so happened I have some material here that I looked up and George wasn't looking. A fast Fourier transform, or FFT, is an algorithm that computes the discrete Fourier transform of a sequence, or its inverse. Fourier analysis converts the signal from its original domain, often time or space, to representation in the frequency domain, and vice versa.
Ah, that last thing you said there.
And vice versa?
And vice versa. If we go back and look at that question again, they only gave you the choice of converting a digital signal from a time domain to a frequency domain. You could also do a frequency domain to a time domain. That wasn't one of your choices. So it goes both ways.
Yeah.
Yep. They didn't give you the other option, which is good because then you'd really have a difficult time settling on one answer. We're going to be back in just a moment.
Got cabin fever? Look no further. Spring is just around the corner, and Icom has what you're looking for. Our top quality base stations, mobiles, and handhelds are perfect for working your favorite bands inside the ham shack or venturing out this spring. Icom's newest FM transceiver is the ICV3500, and it's ready to hit the road whenever you are. With a compact body and simple interface, this radio is a must for those looking for a long-range mobile with a fresh look. Go further with 65 watts output and get louder with 4.5 watts of audio with the ICV3500. The rugged Icom IC-T10 portable meets or exceeds standard military testing. With an IP67 waterproof rating, the IC-T10 can withstand any field activities ahead. Hear any transmission and listen to FM broadcast with a loud 1500 milliwatt speaker. The IC-T10 is an excellent choice for any bug-out bag. The IC7300 is a high-performance, innovative HF transceiver with a compact design that will far exceed your expectations. This innovative HF transceiver digitizes RF before various stages, reducing inherent noise in different IF stages. With RF direct sampling, the IC7300 changes the way entry-level HF is designed. The IC705 is a perfect sidekick and QRP companion. Base station features and functionalities at the tips of your fingers in a portable package covering HF, 6 meters, 2 meters, and 70 centimeters. This compact rig weighs just under 2 pounds with RF direct sampling for most of the HF band and IF sampling for frequencies above 25 megahertz. The perfect accessory for the IC705 is the optional backpack LC192 with a special compartment for your IC705 and room for accessories. The ID52A is a VHF-UHF dual bander with D-Star and FM dual mode functions and is the first handheld amateur radio with a full-color 2.3-inch waterfall display. This radio supports conventional FM communications and D-Star simplex, repeater, regional, and worldwide calls over the D-Star Internet Gateway. Send photos over D-Star with a connected Android device. The ID52A is a perfect companion to the IC705. Both use compatible batteries and headsets, and you can also use the same Android app for D-Star operation. Learn more about these and all the great Icom radios at icomamerica.com/amateur. For the love of ham radio.
What do you say we give away something?
Wait, what is this? How about this?
You pulled it right out of your pocket.
Yeah, just so happened to have an extra Ham Crew t-shirt from Icom. Looked just as good when you leaving the Ham Fest as you did when you got there. Got the same thing on the front and the back. I need a new line.
Yeah. Well, there's no way to put it on backwards.
That,
Well, I guess you could. There's a tag, but if you put it on backwards, it
it's
won't
not
matter.
the end of the world.
Right.
There's a good chance nobody will catch you.
So if you'd like to win that, along with whatever else Jesse can stuff in the box, and he stuffed some other neat things in there.
Yeah.
Because we hear from the winners, and they like what Jesse's putting in the box. So you just never know. If you'd like to win it, all you got to do is have a name and an email address, and send us an email to hamcollege@AmateurLogic.TV. You can put a note in there if you want to.
The only requirement's pretty easy.
And you drew one via random drawing right during the break there.
I did. The winner this month is Bill K8WWS. And he's got a little note in here that says, I want to look cool too. And you will. Is it okay to operate AM afternoon? Signed Bill K8WWS.
Sure.
Why not?
Yeah. Anytime. Just pick out a good spot in the one of the AM windows to operate and go after it. Depends on what band you're on. You're going to have more success on some bands than others in the afternoon. 80 meters may not be great in the afternoon, but hey, 40, 20.
Yeah.
Yeah. There's people operating AM.
You know, I've never really done much with AM. When I first got my ticket, I lived in Missouri. I played around on there a good bit and listened around. I don't think I ever made a contact on it. Have you?
AM? Oh, yeah. Yeah,
I've listened a lot.
Well, I haven't lately, but I have worked AM a number of times, and yeah, to me it's nostalgic because I worked in AM radio when I was 16, and I've used to do a lot of DX and still do some DXing on the AM broadcast band. And it's something about the sound of AM. It's a lot different than sideband. Yeah, your signal is going to go further with the same amount of power on single sideband because you've concentrated it all, into just one sideband. But the AM has got a certain characteristic sound, a little higher quality.
What is a function of decimation? A, converting data to binary code decimal form.
B, reducing the effective sample rate by removing samples.
C, attenuating the signal.
Or D, removing unnecessary significant digits. What is
I've
meant
heard that term before.
by decimation? Yeah. I know the answer to this one. You ever look at your SDR Uno software anymore? Ever play
I haven't
with
in
you?
a while.
Yeah. There's a decimation
Okay.
option on there where you can choose.
Well, that makes sense because this is all kind of about that type stuff.
Yeah.
Tonight's section.
What is a function of decimation? A, converting data to binary code decimal form. What the heck would binary code decimal form mean?
You know,
That's
it's like
two different
one,
number
it's like
systems.
1 dot 1 dot.
Can you?
I have no idea.
Yeah, I mean neither. C, attenuating the signal. Well, yeah, I could see where you might think that. D, removing unnecessary significant digits. Would a significant digit ever be unnecessary? No, if it's significant, how could it be unnecessary?
It's insignificant.
Yeah. B, reducing the effective sample rate by removing samples. That's the answer.
I could see where that would fit right in with this, the topic of the evening.
Let's see, chat room. Man, they know this stuff. It is B. Reducing the effective sample rate by removing samples.
We got a B, C, D in there.
Why would you want to do that?
Now, would you want to do that?
I'm glad you asked. There's a good reason for doing that, and that is you're making the data that you're dealing with smaller. If you're eliminating unnecessary samples, then
compression.
you got less numbers to deal with. Your computer won't be taxed as much, or your CPU or DSP or whatever you're using. That means it can process stuff faster. Maybe you can display a wider bandwidth. You know, things are more efficient. If you've taken every single sample and and some of them are going to be insignificant, really not going to change your outcome. You're processing more data than is absolutely necessary, which is okay if you've got the power to do it.
That's pretty much how MP3 files work too, I think. It's
Yeah,
more
yeah,
complicated
it's
than
more
that, but you're
complicated,
throwing
but
away
yeah.
bits that you supposedly
Yeah.
can't hear.
Yeah,
But you can hear them. You can tell when they're gone.
Why is an anti-aliasing digital filter required in a digital decimator? A, it removes high-frequency signal components that would otherwise be reproduced as lower-frequency components.
B, it peaks the response of the decimator, improving bandwidth.
C, it removes low-frequency signal components to eliminate the need for DC restoration.
Or D, it notches out sampling frequency to avoid sampling errors. Anti-aliasing. It removes high-frequency signal components that would otherwise be reproduced as lower-frequency components. I'm going with A.
I'm going to agree with you.
What's everybody else agreeing with? A.
A. These questions are a lot easier, apparently.
When I first glanced over the list of them, they didn't look easier.
No, they didn't, did they? But you got it.
But I didn't run down through the answers either, so.
Yep.
It just goes to show you, even though it looks pretty daunting, sometimes sit there and reason them out. You can make your way through them.
Yep. It's sort of like, I'm not even going to get into it, but image signals on a receiver. If you've got a real strong signal, you might have an image a little bit off frequency from there that's generated because the strong signal is there and it's hitting your front end so hard that you've got an alias of your original signal as an image down there, and if you need to filter that out, same difference. That would be an analog example, more or less. But okay.
What aspect of receiver analog to digital conversion determines the maximum received bandwidth of a direct digital conversion SDR? A, sample rate.
B, sample width in bits.
C, sample clock phase noise.
Or D, processor latency. What aspect of a receive analog to digital conversion determines the maximum received bandwidth of a direct digital conversion SDR? It's not processor latency. It's not sample clock phase noise. It's either going to be A, the sample rate, or B, the sample width in bits. We'll just see. I'm going to say A, sample rate. What do you think?
Yeah, I think so too. Although I could see how you could kind of think it might be B too.
Well, everybody in the chat room said A, so if that's not the answer, we're all
I
wrong.
think it's A.
I think it is too. And it kind of follows along with some of the earlier questions there. The higher the sampling rate, the higher the frequency.
Mm-hmm.
So if you want maximum bandwidth, you want maximum
You
sample
remember
rate.
the sound card SDR things from a long time ago?
Yeah. Yep.
Better sound card, you had better performance.
Well, the more bandwidth you could look at at one
Mhm.
time. What was the name of that thing? I've got one
Soft
too.
rock?
Soft rock. That's it. Yep. So same thing with any of the SDR receivers. Higher the sample rate, the more bandwidth it can process at one time.
You could do that with a regular sound card too.
Oh yeah. What is a regular sound card anymore?
The one that's built on your motherboard.
Yeah, I guess so these days. You can't
Or
hardly.
USB.
It's hard to find consumer sound cards these days.
No more sound blasters.
Last sound blaster I saw was plugged into the USB port.
Really?
Yeah.
Those Sound Blaster ASP cards were awesome.
Yeah.
And
they were
in their day, and that's been
Yeah.
a long time ago. What sets the minimum detectable signal level for a direct sampling SDR receiver in the absence of atmospheric or thermal noise? A, sample clock phase noise.
B, reference voltage level and sample width in bits.
C, data storage transfer rate.
Or D, missing codes and jitter. You're going to have to read that question to me again.
What sets the minimum detectable signal level for a direct sampling SDR receiver in the absence of atmospheric or thermal noise?
All right, so we don't have outside noise sources interfering with it. I'm going to say it's not D, missing codes and jitter. It's not C, data storage transfer rates. Sample clock phase noise, A, or B, reference voltage level and sample width in bits. That's your answer. It's going to be B.
Yeah, that's what I think too.
Reference voltage level and sample width in bits. Okay. Let's see. What's the chat room saying? Oh, they're a little mixed on this one. I think they're mixed on this one. Let's see. And it is. The minimum detectable signal. Well, you're referencing that signal to a reference voltage level. So the lower that reference voltage level, the lower the minimum detectable signal.
Mm-hmm.
If you had a real high voltage level, you couldn't really detect anything very low. And the sample width in bits. The more bits you got, the more ciphering you can do, or the more precision,
More resolution.
more resolution you got.
Well, we just did that with the calculator earlier.
Which of the following is an advantage of a finite impulse response filter, FIR filter, versus an infinite impulse response, IIR digital filter? A FIR filter can delay all frequency components of the signal by the same amount.
B, FIR filters are easier to implement for a given set of passband roll-off requirements.
C, FIR filters can respond faster to impulses.
Or D, all of these choices are correct. This might be my first buzzer for the evening. Which of the following is an advantage of finite impulse response, or FIR filter, versus an infinite impulse? Well, one's infinite and one's not.
That's not one of your answers. That must be E.
It's E. Yeah, that's what it is. It can delay all frequency components of the signal by the same amount. FIR filters are easier to implement for a given set of passband roll-off requirements. FIR filters can respond faster to impulses. Finite. Infinite. I'm just going to go with a guess here. I really have no idea, but I'm going to guess C, and it's probably wrong.
There were a lot of D's being floated about in the chat room, but I don't think it's D. And it is A. There's tonight's first buzzer. You know, it took a long time to actually get to that buzzer.
But I came through.
A lot of buzzers went off all over the place. It wasn't just you.
What is the function of taps in a digital signal processing filter? A, to reduce excess signal pressure levels.
B, provide access for debugging software.
C, select the point at which baseband signals are generated.
Or D, provide incremental signal delays for filter algorithms. What is the function of taps in a digital signal processing filter? A, to reduce excess signal pressure levels. No. B, provide access for debugging software. You know, you would think maybe this is one of those trick answers. You'd think, well, I could tap in here and debug it.
Mm-hmm.
No, that's not what that is. C, select the point at which baseband signals are generated. No. D, provide incremental signal delays for filter algorithms. I'm going to say that's it. I don't know. You got any thoughts?
Not a single thought in this head.
All right. Yeah, we didn't get a lot of answers on this one. Let's see.
Yeah, I think I know why. Usually if they know, they answer pretty fast. If they don't, they're usually kind of hanging back.
Yeah. So we had a few buzzers on that. We had a number of folks get it right. Which of the following would allow a digital signal processing filter to create a sharper frequency response? A, higher data rate.
B, more taps.
C, complex phasor representations.
D, double precision math routines. Double probation.
There's a lot of good wrong answers in this one.
Which of the following will allow a digital signal processing filter to create a sharper filter response? Higher data rate. I don't think so. More taps. Maybe because the last one was dealing with taps and they tend to do such as that. C, complex phasor representations. I'm gonna go with B. More taps. I really don't even know exactly what taps look like on there, but the last question was about taps, and they tend to come in pairs.
But you might not have had the last question,
I know,
so you wouldn't know that.
but I did hear it.
Most people miss this one. I think there was one correct answer in there. There you go. It's more taps. And I had to do some reading on this. Sharper filter response. All right, let's say we got a sine wave here. A really poor looking sine wave. The more points along the line here that we sample it, the more accurate or sharper we can make that filter. So we got what we call taps along in frequency here. And this is a very poor way to explain it, but if I've got this many taps or points along it, then I can kind of approximate that. What if I only had 2 taps here? I couldn't really draw that. I mean, I might come up with something that looked like that, but that wouldn't be right because, this has got edges to it, or it's more of a sine wave.
Mm-hmm.
So the more taps, the better the resolution. On analog filters, instead of having taps, they would call them poles. The more poles in a filter, the more defined or higher resolution it can be. Same thing here. The more taps, the higher the resolution. Marty says it works for him. If it works for Marty and Tommy, that's good enough. It doesn't matter what Mike thinks. Although Mike's the one who said more taps equal higher resolutions. There you go.
There you go.
And that, my friends, is all the questions for tonight. I don't know what the next questions are going to be because I don't think that far ahead.
That's the best policy.
Yeah. These were tough enough, but hopefully we...
I don't think they're going to get easier.
Oh, they might. They might.
You
These
think?
were pretty tough.
There might be a batch or two here and there that are fairly easy, but the extra questions in general, have been pretty tough.
I think going over these questions tonight, I don't know about everybody else, but I have a little better understanding of, the DSP and SDR thing now.
I do.
That's a nice looking Ham Crew t-shirt that you had there.
It is. It's real nice.
But the Hamfest season is here now, and it's coming pretty often, so everybody ought to go register. Just send an email to hamcollege@AmateurLogic.TV. And you might win one of these, but there's going to be a limited number of months and episodes between now and, say, Hamvention. And you might really need to look sharp and impress your friends.
You will need to. You definitely do.
It's a required thing.
It is required.
Plaid, while it's in, always. If you really want to stand out in the crowd, that's all I could come up with.
There are a lot of plaid shirts on the airplanes on the day before Hamvention starts.
So if you didn't want to blend into the plaid ocean,
the plaid crowd,
what could a fella do?
Well, you know what? We got a swag store. You got some cool stuff. You probably look pretty sharp in that. shop.spreadshirt.com/AmateurLogic. You can get t-shirts, golf shirts, caps, cups, hoodies. There's some jackets on there, mugs, all kind of cool stuff. You look pretty sharp walking around Hamvention with that stuff on.
You will. I mean, imagine if a fella come up to you with an AmateurLogic t-shirt and a Ham College hat, holding a mug.
I feel compelled to take his picture.
Yep. You would have to check what he's drinking in that mug. I don't know. It's never happened yet. I'll just put it that way.
No.
Somebody could set a trend there, though.
There's been people out there with the AmateurLogic shirts.
Oh,
and caps
yes.
on.
Yes. but not a shirt and a cap and a mug. We've never
No.
seen anybody yet.
No,
with
I
a
haven't
mug.
seen anybody carrying the mug around.
I shouldn't have said that because somebody will show up there and show me a mug.
Well, that'd be cool if they do.
And I'm completely out of gold PL259s now. I don't have any prizes.
I think I got 2 left. I hung on
Yeah.
to them, but I could bring them.
Well,
But if you get the swag, wear the swag, be sure and look us up when you're out there.
yeah, definitely.
Actually, even if you don't, be sure and look us up.
Yeah. Yep. I'm looking forward to it this year, and I hope to see a number of folks there. I know Mike's going to be there, and he's in the chat room over there, and I know Chip is going to be there.
I'm going to do my very best. I'm pretty sure I'll be there. I should know by the end of this weekend.
Okay.
Counting on it.
Well, I hope it works out.
I don't know about Emil. I saw a comment about him buying the pork chop sandwiches, so he may back out after making that comment.
Yeah. I don't know. Do you know, that right there should have been the clue that he's not coming. If he offered to buy everybody
That's what I'm talking about.
a pork chop sandwich, that would be almost as bad a deal as Andy made that year, that he was going to buy everybody who upgraded to extra a Hawaiian shirt. You remember that?
I don't remember him saying that.
I think he said that one time, and he ended up buying a lot more shirts than he had
Oh, did he?
thought. Yeah, a lot of people took him up on that, but
Yeah.
yeah,
I got an Andy Hawaiian shirt.
yeah, I do too. We miss Andy, so good to think about him every now and then, and
Yeah.
he's always a cheerful fellow.
Oh, yeah.
So if you want to know what's going on in high society, what better place to do it than at one of these locations right here?
All the hot social spots.
Yep. Facebook.com/group/Ham College.
You can follow.
AmateurLogic.
Yep. You can follow us at Ham College on Twitter.
Mm-hmm. Or groups.io/G/AmateurLogic. And there we're just going to post about when the next show is going to be, when that episode is posted. That's pretty much it.
Yeah.
Only late breaking news.
Yeah, so you don't get spammed on there. If you're not a social media person, I'm not that much of a social media person, to be honest with you. I get on there sometimes, check our groups, but the groups IO is pretty good because you find out when all the live streams are, stuff like that.
Well, I kind of check the Facebook just because I don't get a lot of extra junk. Mostly I look at our group there, and got a few friends I like to keep up with. So, yeah. If you want show notes, and why wouldn't you?
We got show notes.
AmateurLogic.TV/wiki.
Yep.
Ham College and AmateurLogic show notes right there. Speaking of AmateurLogic, join us on
March 17th.
March 17th.
St. Patrick's Day.
Yep. Sounds right to me. That's when the next episode. Look, I just spun the battery, and I'm back in the biz again.
You must have wore out one side of the battery.
I guess I did. This is those Energizer lithium batteries that I bought. Not rechargeable batteries, just the lithium batteries. Those things have been a bit odd, I'll just say that.
Yeah,
When
I've
they work.
gone to rechargeables in most everything that'll take it.
And with that, I'll just say join us again at the middle of the month, March 17th, the next Amateur Logic. And at the end of the March, or the first week of April, we'll have the next Ham College right here. Thanks for being here, everyone.
We'll see you then. 73.
73.
About time to turn that air conditioner back
I
on.
think it is. And make the light flash, too.
Oh, yeah.
Well,
My water out of my transparent can. It's not totally transparent. Oh, yeah, it is.
yeah. Depending on where you hold it, that big, can't really do it, can you? I mean, that's just like a ghost, man.
It's just writing on the top. What sets the minimum detectable signal level for a direct sampling SDR receiver in the